Hello and welcome to G Fun Facts Online. Today we are going to talk about a quiet revolution. It happened recently, not with a bang, but in the absolute silence of a sub-zero vacuum chamber in Santa Barbara. For 30 years, physicists and engineers have been fighting a war they looked destined to lose. It was a war against entropy, against the fundamental chaos of the universe. This is the story of quantum computing, and specifically, a new processor called Willow. To understand why Willow is such a big deal, we have to look at the paradox that has haunted this field for decades. In traditional computing, like the laptop or phone you are using right now, making a computer bigger usually makes it better. If you add more transistors, you get more processing power. It is a linear, predictable path. But in the quantum world, the rules are different. For a long time, building a larger quantum computer actually made it worse. Imagine you are building a house of cards. If you build a small tower, it is relatively stable. But as you add more cards, to make the tower taller and more impressive, it becomes exponentially more fragile. A tiny vibration, a shift in the air, or just the weight of the cards themselves can cause the whole thing to collapse. In quantum computing, this collapse is called decoherence. Every time engineers added a qubit, the basic unit of quantum information, to a processor to make it more powerful, they also added noise. They added more pathways for errors to sneak in. It seemed like a trap. To build a computer capable of simulating the universe, you had to build a machine that broke faster than you could actually use it. That paradox effectively ended in December 2024. The Willow processor, unveiled by Google Quantum AI, demonstrated something that should be possible according to the old trends. It showed that making a quantum computer larger can actually make it more accurate. This is a concept called exponential error reduction, and it is the holy grail that researchers have been chasing since the 1990s. Let's dive deep into the tyranny of noise to understand what they actually solved. Quantum computers rely on qubits. These are subatomic pointers that can exist in a superposition of states. They are not just 0 or 1. They are 0 and 1 simultaneously. This superposition is where the magic happens. It allows the computer to explore vast computational landscapes in parallel. But this state is incredibly delicate. A stray photon, a tiny fluctuation in the magnetic field, or even the thermal vibration of a single atom can cause that superposition to snap. The qubit collapses into a regular boring bit. That is quantum noise. For years, the scaling law was brutal. If you had 10 qubits, you had a certain probability of error. If you went to 20 qubits, you didn't just double your power. You exponentially increased the chance that one of them would fail before the calculation was finished. The predecessor to Willow, a chip called Sycamore, was a marvel of engineering, but it lived on the edge of this cliff. It was like trying to solve a complex puzzle while sitting inside a blinking strobe light. You had to finish the puzzle before the light went out, which happened in microseconds. So, how do you fix this? Theorists in the 90s came up with an idea called the surface code. The idea is that you stop relying on individual physical qubits to store your precious data. Instead, you weave many physical qubits together into a grid to form a single entity called a logical qubit. In this grid, some qubits store the data, while others act as spies. These spy qubits, or measure qubits, constantly check their neighbors for errors. If a physical qubit flips due to noise, the spy catches it, and the system corrects it in real time, all without looking directly at the data and destroying the quantum state. But there was a catch. This only works if your physical hardware is already pretty good. There is a specific limit called the threshold. If your physical qubits are trash, grouping them together just creates a bigger pile of trash. The error rate of the individual components needs to be below roughly 1%. If you can get below that threshold, then the magic of the surface code kicks in. If you are below the threshold, adding more physical qubits to your grid suppresses the errors exponentially. For 30 years, this was just math on a chalkboard. With Willow, it became physics. Willow is a 105-qubit superconducting processor. But simply counting qubits is like comparing a nuclear reactor to a steam engine by counting the number of pipes. The architecture is what matters. Willow uses a Z architecture. It is a square grid layout where each qubit acts as a node in a lattice, connected to 4 neighbors. This specific shape is necessary for those spy qubits to do their parity checks. One of the biggest engineering leaps in Willow is something called the tunable coupler. In many quantum chips, the connections between qubits are static. This leads to crosstalk. Imagine trying to have a conversation with a friend, but your neighbor is shouting their own conversation right next to your ear. That is crosstalk. When you try to control one qubit, the neighbor hears you and gets confused. Willow's tunable couplers act like variable valves. They can completely isolate a qubit from its neighbors when it is processing, effectively shutting the door, and then snap open to entangle them when needed. This on-demand connectivity is crucial for high-fidelity operations. Then there is the coherence time, or T1. This is essentially the memory span of the qubit before it decays. The old Sycamore chip had a T1 of about 20 microseconds. Willow has pushed that to around 100 microseconds. That is a 5-fold increase. It sounds small, but in the world of quantum control, that is an eternity. It gives the control electronics enough time to spot an error and fix it before the data dissolves. So, what was the experiment that changed everything? The Google team didn't just run a calculation. They ran a stress test of the surface code theory. They created logical qubits of different sizes on the Willow chip. They started with a small grid, a distance 3 logical qubit. Then they made a medium one, DISTANCE5. Then a large one, DISTANCE7. The hypothesis was simple. If the hardware was bad, the larger grids would have more errors because they have more moving parts. But the result was the opposite. When they moved from distance 3 to distance 5, the logical error rate dropped by half. When they went to distance 7, it dropped by half again. This proved that they were below the threshold. For the first time in history, adding more resources made the system cleaner. This is the moment the rules of computing changed. We can now theoretically build a perfectly error-free quantum computer simply by making the grid big enough. But hardware is only half the story. In October 2025, the team dropped another bombshell called quantum echoes. You might remember the controversy around quantum supremacy back in 2019. Critics said the task the computer performed was useless. It was just generating random numbers. It was like asking a supercomputer to predict a coin flip sequence. Hard, but pointless. Quantum echoes changed the narrative. This new algorithm computes observables of complex many-body quantum dynamics. Crucially, it is verifiable. Unlike previous experiments, where we just hoped the answer was right because classical computers couldn't check it, quantum echoes allow for a measurement of fidelity. And the performance? Willow ran this task 13,000 times faster than the world's most powerful classical supercomputer. This marked the transition from quantum supremacy to quantum utility. Let's take a moment to appreciate the engineering stack that supports this chip. It is not just about the silicon and aluminum. To control 105 qubits, you need massive amounts of wiring going into a fridge that sits at 10 millikelvin. That is colder than deep space. Heat is the enemy. Willow uses advanced cryogenic CMOS controllers that sit inside the fridge at higher temperature stages to manage the data traffic. They also had to solve the real-time decoding problem. Error correction is a data problem. You are measuring error signals millions of times a second. You need a classical computer sitting right next to the quantum chip to interpret those signals and say, "Qubit 43 flipped, flip it back." Willow's control stack achieves this loop in microseconds. So where do we go from here? If Willow is the transistor moment of quantum computing, we are now looking for the Pentium moment. The physics works. Now it is an engineering scaling challenge. To build a machine that can break RSA encryption or simulate a complex enzyme, we need logical qubits with an error rate of 1 in a billion. To get there, we need massive logical grids. We are talking about a processor with roughly 1 million physical qubits. Willow has 105. That is a massive gap. But the path is illuminated. We don't need to discover a new particle. We just need to stack the Willow blocks. We need to figure out how to wire 1 million qubits without heating up the fridge. We need to miniaturize the control electronics. Why does this matter to you? First, there is the security implication. It is still years away, perhaps a decade, but Willow confirms that a cryptographically relevant quantum computer is possible. This validates the threat known as store now, decrypt later. Hackers could be stealing encrypted data today, waiting for the day a Willow successor can crack it. This is why the world is rushing to migrate to post-quantum cryptography. Beyond security, we are entering the molecular age. Classical computers cannot simulate the quantum mechanics of caffeine, let alone a complex protein. Willow's successors will allow us to design batteries with 10 times the energy density, room temperature superconductors, and catalysts that can capture carbon from the atmosphere efficiently. And then there is artificial intelligence. Quantum computers can process high-dimensional vector spaces, the native language of AI, more naturally than GPUs. We may soon see quantum neural networks training on these chips to solve optimization problems that baffle current AI. History will likely look back at this period, late 2024 and 2025, as the turning point. Before Willow, quantum computing was a very expensive, very cold maybe. With the achievement of exponential error reduction, the maybe became an inevitability. The threshold has been crossed. The noise has been tamed. We are no longer asking if we can build a useful quantum computer. We are simply asking how fast we can build it. The Willow processor is not just a chip. It is a proof of concept for the future of humanity's computational capacity. The error bars are shrinking, the fidelity is rising, and the quantum age has finally, truly begun. Thank you for listening to G Fun Facts Online.